Welcome to the micro communication course. Today we will talk about that TMU solution. Now, in a TMU solution, if you see that we are propagating in the z direction, in that case, the component of Hz is equal to 0. That is called as a TMU. Now, if the component of Hz is equal to 0, then a Ez component is present in a TMU solution. The Hz component means what? Direction of propagation of wave. It is about a z direction of propagation of wave, and that along with that there is a z component. That z component is longitudinal component. So now we say that Ez component is also there. Okay, Ez component is present in a TM wave. That's why Hz is a zero. So that wave, if that Hz is zero and Ez is present, that wave is called as a TM wave. Next, to obtain that a TM wave solution equation, we need to consider the equation. So earlier we have derived the equations for the T wave. I'll just write those equations directly here. So we need to find out the equations for the Ex, Ey, then Hx, Hy, and then we got the equation for the Ez. So if you take the same here, I'll directly write the equations here with because Ez is present, we'll write directly the Ez first. It has the epsilon 0 sine of m by x by a sine of n pi y by b. Now we know that a kx is equal to m pi by a. That we know. Already we have seen that for the electric field intensity, for the t mode of a propagation, we obtain that a kx is equal to m pi by a, and we say that a ky is equal to n pi by. Now this m and n, m means what? A half wave variation along with this a side, this width side, and n means what? A half wave variation along with the height side. Since our rectangular waveguide, we say that rectangular section here. So this one is about the width, that is about the width of the waveguide, and this one is about the height, is nothing but the b. So half wave variation along with a and half wave variation along with b. So according to that, kx and ky component comes. Here we have considered that wave is propagating in a z direction. So that's why this is about a wave. This is about a rectangular waveguide. So your wave is propagating in the z direction. We have the component of electric field, component of a magnetic field, the component of electric field Ex, Ey, Ez, magnetic field Hx, Hy, Hz. So if you see that, we say that Ex, Ey, okay, Ez likewise, so X, Y, Z component. Similarly, we have the magnetic field, it has Hx, Hy, and Hz here. Now these components are there. So direction of propagation is Z. So means wave has a component along with the direction of propagation. So now we talk about the TM wave. TM wave means what? A transverse magnetic wave. Okay. So transverse means what? A perpendicular one. Okay. Transverse magnetic wave means transverse. All the field components are a transverse only. There is no longitudinal component. That's why it has a X component, Y component. Z is a component. It is propagating along with. That's why Z is equal to 0. Okay. We say that Z is equal to 0 here. So means that Z component is along with this direction of propagation, that is 0. So only it is what? A transverse component. So that's why it is called as a transverse magnetic wave. in a T wave, that is Ez is equal to 0. That is called as transverse electric wave. And this M and N specifying the variation of a field along with a and a B M. So that's why we say that your wave is what? A TM wave. So it has a M and N specification. And this M and N is nothing but what? A half wave variation. You can say that it is nothing but what? M is already we specify that it is about the half cycle variation. So how many number of half cycle variations are there in the given particular waveguide? So N, how many number of a half cycle variations of magnetic field that along the B side, along the A side. Okay, likewise. So half a variation, half cycle variation along the A, half cycle variation along the B. So that is about that represent that M and M. So similarly, if you see that a T wave, so T wave it has the M and N component. Now we say that again here the same. It has half cycle variation along with A. So it is again the half cycle variation along with the B here. So that is about the variation of half wave variation along with the A and B. If you consider the both M and N, okay, if that M and N are there, both should not be at 0. So means what happened? Tm 00, Tm 00 likewise. So this M and N both cannot be a 0 here. So either M or N can be a 0, but both cannot be a 0. Both can be equal, but they are non-zero. M equal to N. If M is 1, N is 1, okay. But M cannot be a 0 and N cannot be 0. Both cannot be a 0. So means we say that both are non-zero components. So now for the TM wave solution, we should know that what is the EZ component first. Once we obtain that EZ component, from this EZ we can find out that EX, EY and other components. Okay, so now we can write the expression of a EX, EY here. We'll write here EY here. That is equal to what? Gamma by Kc square N pi by B here is 0 sine of M pi x by A. Instead of that, I'll write Kx here. Kx means for M pi A. Kx x here and a cos of N pi by B. I'll write Ky y. Okay, so that we can write in a simple way. Kx is equal to what? M pi by A. Ky is equal to what? N pi by B. Then Ex is equal to gamma by Kc square M pi by A here is 0 cos of M pi x by A. Sorry, write Kx here. Then sine of Ky by y. Okay, that is about Ex and Ey term. Then Hz we say it is a 0. Then it has only a what? A Hx and a Hy term. So you can write Hx here. J omega epsilon Kc square N pi by B is 0 sine of Kxx to cos of Ky y. Then we say that Hy is equal to minus J omega epsilon Kc square M pi by A here into E0 cos of Kxx into sine of Kyy. Okay, now this one is about the equations for the Hx, Hy. Now, from this we say here, the component of what? Z is equal to 0. Okay, because it is about a transverse magnetic field. And this M and N, both are nothing but what? Half cycle variation. And that M and N for the given mode, for the TE or a TM mode. Suppose I am saying that that is about our TM mode, then it is about a subscript M, small m and N. Subscript M and N. That M represent that a half cycle variation along with A, N represent that half cycle variation along with a B here. But both the M and N are not equal to 0. Okay, just remember that. So M can be start from the, what we can say that for the TM mode to be exist. So M equal to 0 or N equal to 0, that provides you what? That there will be a zero field intensity inside the waveguide. Means what? So here for the TM mode, M will start from the 1. Okay, M, the value of a M for the given particular mode, value of a M and N will not be a 0. To exist the mode, either M will be 0 or N will be a 0. Okay, so likewise, you can consider that we say that we have the M and N, these are the values here, and N will be what? 1, 2, 3. So means for the TM mode, M and N, this M subscript, whatever we say that M and N, it will be either 1. Okay, it should not be a 0 here. But in the case of a TM mode, so M or N can be start from the 0 here. So now other components. Okay, so now we say that a TM mode or a T mode here. So the field component that we have obtained earlier for the T mode of propagation there, that is about a cutoff frequency. Then we obtain that the propagation here, propagation constant. Then we obtain that a phase velocity. Then we obtain the group velocity, and we obtain the guide wheeling. All these components that we derived for the T mode are equal. Okay, same. Okay, for the T mode, whichever the equations we have derived, that equations are same for the TM. You as it is, we can use that equation for the cutoff frequency, propagation constant, phase velocity, group velocity, and the guide wavelength. We can use the same equation for the TM. Okay, there is no change in this equation. So that's what why we are saying. So that modes, whatever the equations we have derived here for the TM mode, that equations are same for the TM mode. Only there is a variation. That variation is about what? There is a change in the equation that is about a characteristics impedance. So characteristics wave impedance for the TM mode is different as compared to the T mode. For the T mode it is different, for the TM mode it is different. So characteristics impedance for the TM mode is different from the T mode. So it is about the EX by HY, or we can say that minus EY by HX, then beta by omega epsilon is equal to eta by beta by, we can say that is about K, or we can write the form of frequency here, eta under root of 1 minus fc by f bracket square is equal to 377 lambda 0 by lambda 0. So if you compare that a characteristic impedance of a T mode and a TM mode, Then we can write the expression with comparison of a characteristic impedance here. So ZW for the TE mode into ZW for the TM mode is equal to eta square. Okay. ZW means characteristic impedance of a TE mode and characteristic impedance of a TM mode. If you multiply both, so then you will get the that intrinsic impedance. Okay, that is about the eta square. That eta square, that we can say that it is about the value of 377 ohm or a 125 generally we say for the free space wave propagation there. So we say that here, so that for this particular TM modes of a propagation there, if you conclude here for the TM mode of a propagation, so M and N cannot be a 0. We can say that M will be 1 and N will be a 1 here. Okay, means we can say that M start from the 1 and start from the 1. Okay, so then we'll get the different modes of a T mode of a propagation there. So we see here for the other components for this mode here, that is about the other parameters for the rectangular waveguide. What do you mean by a dominant mode? What do you mean by a degenerate mode? Okay, so we will see few terms. Okay, so with respect to the T mode and a TM mode, you just remember that for the T mode of a propagation or a TM mode of a propagation, you just remember that for a rectangular waveguide, this one is about a rectangular waveguide, is supposed to be considered for the given rectangular waveguide. So this one will always say A and this is about a B here. So A always greater than B. Okay. So these are about the dimension. Dimensions of waveguide A is always greater than the B. Or if you talk about that value of A, it is to be as compared to the B. So generally people are saying that A is equal to twice of B. Okay, A will be a twice of B. Okay, that is about the condition. Okay, for some condition. Now, right now, you just remember that for any kind of a guide, we need to calculate that a characteristic impedance or a cutoff frequency for the given guide. So we should know that the dimensions of a waveguide. So based on the dimensions of a waveguide, we can obtain the various parameters of the waveguide. Now, A is greater than B. This is dimension that is about the here width of this waveguide, and this one is about the height of the waveguide. Okay, so we say that this is belongs to the width here, and this belongs to what? Height. Okay, this one is about the height. This one is about the width. A width is always greater than the height here for the given particular waveguide. And then we say that a T mode of a propagation is what? M and N. So T, M, N, or we say that a T, M, M, N. So that M, if you use the M word here, that M is nothing but what? A half cycle variation. That is about the half cycle variation. Okay, half cycle variation. Okay, in what? In the direction of A here. Okay, that is about we can say that a half cycle variation for this M here. So even if we supposed to be consider that, so along with a, we say that generally will not talk about the A. Okay, so I'll just talk about in a or theoretical way. That is about the direction of a wave, whether it is a x direction or a y direction. Okay, I'll just say here. Again, redraw the diagram now. It's about your rectangular waveguide now. supposed to say that this is about your guide. This is about the z direction. Okay, so this is about the z direction. Wave is propagating in the z direction, and this one is about your x, and this one is about your y. So means along with a width, or we can say that x direction, along with a y, or we can say that along with this height here. Okay, it will direct it your half your variation, half cycle variation. So M say that how many number of half cycle variation. Okay, just like I half cycle variation in the direction of x, or number of number, that is a M is nothing but a number, that is the number of half cycle variation in the direction of x. Similarly, n is equal to what? The number of half cycle variation in direction of y. Half cycle variation in the direction of x and direction y. This is one. Half cycle variation in the direction of x in the direction of the y. That is about the TMN or TMMN. M and N both are same, except that the values of M and N for the T mode it will start from the zero. For the T mode, M and N will start from the zero. But for the TM mode, that mode is to be exist inside the waveguide. So the value of the small m and n, that will be not zero. It will start from the one. Okay, one, two, three, likewise. So for the T mode, it will start from the m will start from the zero, or n will start from the zero. But for the TM mode, mode is to be exist inside the waveguide. So m or n, either m or n for the TM mode will not be zero there. Okay. Then there is no exist in the mode in the waveguide. Okay, if that both are zero. So we say that variations. Okay, if you remember that half cycle variation of the x in the given direction. So for the given waveguide here, this is about the x here. So I supposed to be considered that this is about the wave is propagating in the z direction, and we have the component of x, that is about the electric field, component of y, that is about the magnetic field. Suppose I'm saying. So in that case, so what will be the variation? Okay, what will be the variation? Now I say that x variation. X variation, we supposed to say that electric field component along with the x. Suppose this one is about the half cycle, it is about a one. So half cycle variation is about a one half cycle variation. So in that case, m will be a one. Okay, if it is about the half cycle variation, we say it is about the one. Then in that case, m is equal to one. If supposed to be, I am saying that the half cycle variation along with this b direction, so n will be a one. So likewise, we say that a modes, various number of a modes. So now, since we are talking about that there are the various number of modes, so we talk about that another, okay, other field component, okay, other component. Okay, we'll come again to this topic about that modes and all. We talk about that first of all that dispersion in a waveguide. Okay, now dispersion in a waveguide. That is about dispersion in waveguide. Now generally we say that a dispersion means what? There is a small delay, okay, propagation delay. And that propagation delay, how that propagation delay occurs? Because we say that we have the waveguide now, and we are supposed to be consider that your field components are propagating. Okay, so from one end to the another end. This is about your rectangular waveguide. We are supposed to say that input, and we are supposed to take a output here. Okay, so now when we are supposed to be consider that wave is propagating from this here. Okay. So now generally what the phenomena of a propagation inside the waveguide is about a reflection. Okay. And we say that wave is propagating, that is about alpha. Your propagation constant is what? The alpha plus j beta. And there is a alpha 0, attenuation 0. So only we have the propagation constant, that is a beta here. And if you see that beta, that is about a propagation constant. Okay. So for the given particular wave. So we talk about that beta in general is not a linear function of the frequency. If you see the expression of the beta here, so in that case we say that it is not a linear function of the frequency for the waveguide propagation. So when we say that wave is propagating there, so there is a propagation. So that's why for the given wave, it has some phase velocity and a group velocity. Phase velocity, okay, that is about for a given particular wave, and we say that a group velocity. If you compare for a given particular waveguide, the phase velocity and group velocity will be different. So group velocity, that is nothing but what? That is about a number of frequency component propagating in a group. Okay, different frequency component, they are propagating in a different group, they have a different velocity. So generally we say that there will be a variation in the for a given particular wave. There is a variation in the what? A phase velocity and group velocity. With respect to what? With respect to a frequency. Now, in general, we say that we have the wave is propagating here. So then, whatever the signal is propagating, it has a different frequency component. And this different frequency component, they are propagating through the waveguide. They have the different velocity. If they have the different velocity, then wave propagating from one end to the another end, we say. So that different frequency component reach at this another end, or we can say that at the load end, at the different instant of a time, because of they have the different velocity. So because those component reach at the different instant of time, so this particular component exhibits what? A differential propagation delay. Means if you consider that the original signal we supposed to be transmitting, when we reach at this particular end, at the another end, the original signal at the load end, because of the differential propagation delay, that could not be reconstructed. Okay, because of that propagation delay. And so that's why what we can say that because of that propagation delay, that signal, original signal at this particular end could not be reconstructed. We cannot be reconstructed there because there is a distortion. Distortion of what? Whatever the signal we transmitting here. And that particular distortion occur at the load end, that is called as a waveguide dispersion. And that waveguide dispersion is nothing but what? A phenomena of what? A delay, because of the delay there. Because of that differential propagation delay. Okay, differential propagation delay. And that can be calculated here. Okay, that dispersion is nothing but a delay here. That is about a differential propagation delay. So that can be calculated per unit length of the guide here. So that is a delta t here is equal to what? It is nothing but what? Whatever the group velocity variation that we supposed to be considered, that is about a maximum here, and a group velocity that is to be considered, that is about a minimum variation in the group velocity, that is about the maximum and minimum. Now how this occurs? Maximum because of that frequency component. So frequency component at this maximum it will be minimum. Frequency component at velocity if it is minimum, that is about the maximum there. and then we will get the dispersion. That is about a differential propagation delay. That is nothing but a dispersion in the waveguide. So this maximum is nothing but for minimum frequency. Sorry, maximum for the minimum frequency, and this minimum group velocity, that is for the f maximum. That is for the maximum frequency in that particular specified band. Okay, so that is about, we say that a dispersions in the waveguide. Then another component, that is about a dominant mode. So dominant mode in a waveguide. So the mode which has a lowest cutoff frequency, mode which has a lowest cutoff frequency. Now to obtain the, what do you mean by this dominant mode? So we need to calculate that a cutoff frequency of the signal. Okay. So now, so then we should know that what mode is propagating. Okay, right now we are not talking about the only specific. So that's why the cutoff frequency, we need to see that for the TE mode or a TM mode. So then again, okay, I'll consider that for the TMN and a TMMN. That MNN half a variation, cutoff frequency is same. Okay, FC. That equation or expression of the FC is same. But at what value of this M and N, so FC will be a lowest. Okay, that cutoff frequency means what? A cutoff frequency means what? A lowest cutoff frequency that is propagating through the waveguide. So that generally we say that a cutoff frequency is depending upon that the dimensions of the waveguide, that is physical size, that is about A and B. And then at what value of a M and what value of a N, we will get the FC lowest. Okay, if you talk about that, so for the given dimensions, we generally say that A is greater than B. We'll talk about that. A is always greater than the B. So then what value of a M and N will get the lowest cutoff frequency. And that is called as a dominant. So we say that M is equal to 1, N is equal to 0. Then we will get that for this particular mode, we'll say that whether which mode is there, because M is equal to 1 and N is equal to 0. Whether it is a T mode or a TM mode, it is a T mode. Because a T mode, in a T mode, M and N will start from the 0. But in the case of a TM mode, if we talk about that TM mode, okay, so we say that TMMN mode here. So M will start from the 1 here. 1, 2, 3, like that. 1, 2, 3. Then here 0 comes. Okay, 1. M is equal to 1 and N is equal to 0 means 0 comes. That belongs to the team. Because M is or N, any one can be a 0 in a T mode. But in the case of a TM mode, M or N both cannot be 0. So this mode, if M is equal to 1 and N is equal to 0 means what? It is about a T10 mode. So at a T10 mode, we will get that mode which has the a cutoff frequency. It is about the lowest cutoff frequency, and that mode is called as a lowest order mode. Okay, even that order is again the lowest. So it has a what? We can say that lowest order mode as well as it has a lowest cutoff frequency, and that mode is called as a dominant. So dominant mode means what? It has a lowest cutoff frequency as well as it is a lowest order. So that mode is called as a dominant. So here in this case, m is equal to 1, n is equal to 0. So T10 mode is the dominant mode. T10 mode is the dominant. So in this case, A is always greater than the B. But generally, if you see that, we will get that a lowest cutoff frequency. Okay, so when that this condition A is greater than, because that is about the rectangular waveguide, that width is to be higher. That's why A is greater than 1. Okay, so that is about a dominant. Then, and we know that, I'll just say that FC is equal to what? 2 under root of mu 0 epsilon 0 here. Okay, suppose directly we consider under root of m by a bracket square plus n by b bracket. Okay, so now this one is nothing but what? 1 by mu means what? A c. Okay, so I'll just say that c means what? 3 into 10 to the power 8. 1 by mu e. Mu 0 epsilon. That is c equal to 3 into 10 to the power 8. Only our aim is about to concentrate on these values of a m and n. I'll just write c by 2 under root of m by a square plus n by b square will get the cutoff frequency. Now I say here m is equal to 1 and n is equal to 0, that is about the dominant. So now you put that m is equal to 1, that is 1 by a. Okay, 1 by a bracket square, n is equal to 0, this is term 2. Okay, it will be 0. Now if you consider that a WR90 standard, okay, in that case, we can say that a is equal to what? 2.25. Okay, so that we just earlier we talk about that the value of that a. Okay, what will be the value of a for the WR90 standard? And you can calculate that for the WR90 standard. So what will be the value of this WR90 standard? What will be the value of a FC? So now A and B, these are varying based on the dimension. Suppose I am saying that A is equal to B 2 and B is equal to 1. For this, if I calculate that FC here, so this will be what? M is equal to 1, 1 by 2. Okay, this one is about 1 by 2. That is about 1 by 4 here. And then we can, if we take out here, it will be 1 by 2. Okay, so means what? 3 by 4. Means 3 into 10 for 8 by 4. Likewise, so we will get that lowest dominant. So it is depending upon that a dimension. So we should know that at what value of this guide, okay, that A and B, so we'll get the dominant. Okay, that's about a dominant mode or a cutoff frequency. That will be a lowest. So next we see that a degenerate. Now a degenerate mode means what? We earlier say that the mode that it has a lowest order mode. Okay, that is called as a dominant. But some modes are there that modes are higher order. Okay, now the modes can be a higher order mode. Higher order means what? T2, okay, T20, 221, T22, likewise, or TM21, TM22, likewise. That modes are called as a higher order. So now At some higher order mode, some modes having the same cutoff frequency. Okay, at higher order mode, they are having the same cutoff frequency. And that higher order modes are called as a degenerate mode. Okay, there are some higher order modes. That higher order modes, they have the same cutoff frequency. Okay, some higher order modes, they have the same cutoff frequencies. Okay, they have the same cutoff frequencies. That modes are called as a degenerate. And in that particular case, for the T and a TM, okay, for the TE and TM, we can supposed to be consider that TMN, TM, MN here. The conditions are what? That A is not equal to B. It is not, it should not be equal to B here. And again that the condition is what? M or both, we can say that M is not equal to 0 and N is not equal to 0. Okay, so that is about the condition. But if you consider that the wave is a square waveguide, if it is a square waveguide means what? A is equal to B. Okay. If it is a square waveguide, then there may be a possibility to generate the degenerate mode. Means that higher order mode having the same cutoff frequency. Okay, so that is called as a degenerate mode. So it can be we can say that a T12, T21, TM12, TM21. If it is A is equal to, in that case, that mode having the same cutoff frequency. So that is about, we can say that these are the higher order mode. It has the same cutoff frequency. Okay, so in condition that A is equal to B. So this is about, so we can say that these modes are called as a degenerate. Even if A is not equal to B, so some modes are generated. That modes are called as a degenerate mode. So we talk about that a different modes, dominant modes, and all modes here. So now I just consider here, supposed to be, I am saying that T, I mean mode here. If M is equal to 1 and N is equal to 0. So means we say that it is about a T10. For the T10 mode, M is equal to 1 means if you consider that a rectangular waveguide, so there is a electric field intensity at a center will be higher. Means half cycle variation along with this. So that is about a 1 here. Okay, if it is a T20 mode, I supposed to be considered that is about a T20 mode. So in this particular case, for the same rectangular waveguide side here, so we have the two half cycle variation. We have the two half cycle variation. So in that case, here it is about the one half cycle variation, but here we have the two half cycle variation. Okay, here is about the two half cycle, one half cycle, another half cycle. That is about a TE20. If it is a 30 mode, likewise a 30. So likewise, we have the half cycle variation for the M. So similarly for the N. So in this case, here we supposed to be consider that there is a magnetic field, likewise. Magnetic field component will be likewise. Okay. So electric field and magnetic, both the components are there. E field component as well as the magnetic field components are there. But if you see the cross-sectional view, it will be different for the different modes here. So that is about for the any view here. If you talk about that, so then for the T10 mode or a T20 mode, your wave will be looks like. So we should know that in which direction your wave is propagating there. So that's why I already draw that direction of propagation of wave, and I say that a uniform plane wave it is propagating. Okay, so we have the field component that is about, we can say a electric field component here. I just consider that a uniform plane wave here, and then we say that we have the magnetic field component likewise. Okay, so now from this, we say that this one is about your, I say that x direction is about the electric field component, and this one is about the y, this is about the magnetic field component. That red is about the magnetic. So this way your uniform plane wave is propagating in space. So now here we say that wave propagation in the z direction. Wave is propagating in the z direction. So from this waveform, we can say that electric field has the x component, magnetic field has the y component, and wave is propagating in the z direction. So for the transverse nature of a T mode, we say that Ez is equal to 0. Ez equals to 0. That is about a T mode. For the TM mode of a propagation, Hz is equal to 0. And from this waveform, if say that electric field component along with X and magnetic field component along with a Y there. Now these components are present when your wave is propagating in the space. So that's all about your